Hi, this lecture is about 2D rendering. Let us consider the rendering problem when the virtual world is two-dimensional, objects are in a plane. The virtual world should be represented by numbers, for which we need a world coordinate system. A convenient reference system is a Cartesian coordinate system with an origin and two axes where a unit is also defined. With a pair of numbers, points can be identified, which can form primitives by adding topology information. For example, we can say that these points define a triangle. Primitives given material properties, which are usually include the color. The rendering process takes a photograph of the virtual world and presents the photo on the computer screen. The rectangle of the photo is called the viewport. Pixels on the computer screen are identified in screen coordinates. The unit of the screen coordinate system is the pixel. To implement the photographing process, we introduce a camera in the two-dimensional world. In 2D, the camera is just a rectangle called the camera window. This rectangle has edges parallel with the coordinate axes. Similarly, the viewport has edges that are parallel with edges of the computer screen. Rendering finds a correspondence between pixels of the viewport and the camera window. This correspondence can be established from two opposite directions. We can start the process in the virtual world, transform objects one by one to the screen, and find the color of individual pixels that are covered by these transformed objects. This approach is called object-driven. Alternatively, we can start the rendering process at the pixels of the viewport when the method is called pixel-driven. Each pixel is transformed back to the world, and the object containing the transformed point is identified. The pixel color is then the color of the identified object. If more than one object contains the transformed point, for example in this figure, this is the case where the green fish overlaps the yellow wall. In this case, we select that object which has the higher priority. Note that in popular drawing packages, actions like bring forward or send back manipulate the priority of objects. The core of a pixel-driven algorithm is the containment test. That is the determination whether a point is in the set of the two-dimensional object. If the object is defined implicitly, this is usually equivalent to the evaluation of the implicit equation for the point to be tested. If the boundary of the object is defined by a parametric curve, whether or not a point is inside should be determined by counting how many times the boundary is crossed until infinity is reached from the tested point. For example, here, this number is an odd number, which means that the point is inside. If this number were an even number, the point would be outside. Here we show the implementation of a simple pixel-driven 2D drawing package. Object is the abstract base class of all objects. It has a color, which will be copied to the pixel color if this particular object is visible in that pixel. Additionally, it has a pure virtual function called in that checks whether point R, given in the world coordinates, is contained by this object. The implementation of the in function depends on the type of the object. Therefore, different types are derived from the base class object, and in is given a particular implementation for which type-dependent parameters may be needed. For example, the circle is defined by the center and the radius. Based on these parameters, the in function checks whether the square distance of point R from the center is smaller than the square radius. If it is smaller, the point is inside. In case of equality, the point is on the boundary. If the difference is positive, the point is outside. Half plane has a line boundary defined by a position vector R0 and normal vector n, and we assume that the normal vector n points outwards. Thus, substituting a point R into the equation of the line, the sign of the result tells us whether the point is in the outer section, which means that the dot product is positive, on the boundary line when the dot product is 0, or inside when the dot product is negative. General ellipse is based on the geometric definition of the ellipse. This is the set of those points for which the sum of distances from the two focal points is less than a constant c. Parabola is also the direct implementation of the geometric definition. We are talking of a set of points for which the distance from the line called the directrix is greater than the distance from its local point. The scene is a heterogeneous collection of objects. We use the list since deletion and priority management require the dynamic arrays and insertion of elements. We have a special data member to show the picked or selected object that is the target of the future operations. Add adds a new object to the list, and the new object becomes the selected one. Now, this is the typical strategy in drawing packages. Pick takes the pixel coordinate, transforms it back to word coordinates, and tests objects for containment of this point in the order of their priority. If an object is found, it will be the picked one, and we terminate testing since we need that object to the picked one which is in front of the others. Bring to front function moves the picked object to the front of the list, that is, gives the highest priority to it. Send to back and delete are not shown here because their implementation is very similar. Send to back would move the picked object to the end of the list, delete would simply erase it. Render computes the two-dimensional image array by computing the colors of the pixels. Each pixel is visited in a double loop. The pixel is transformed to word coordinates. Objects are tested for containment test of the transformed point, selecting the one with maximum priority, if more than one object contains the point. The selected object's color is written into the pixel. The pixel-driven solution is simple and elegant, however it is too slow. Interactive frame rates are impossible even with moderate number of objects. Therefore, we need another strategy as well. Let me give you a short presentation. So we already have a virtual world containing half planes, parabolas, ellipses, and very many circles. And we can click on them. The picked object changes its color to black, and we can make various operations with selected object. For example, we can send it back. This goes also back, 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 and so on. We may delete objects, so I can purge circles from the big green circle. The camera can be manipulated. I can pan the camera or zoom in or zoom out. So it gives the functionality of a sophisticated drawing package. I just delete objects. The only problem is here. The rendering time is 124 milliseconds, so it's far from being real time, although we have just, say, 100 different objects. Object-driven 2D rendering is a sequence, also called pipeline, of computation steps. We start with objects defined in their reference state, which can include points, parametric or implicit curves, 2D regions with curve boundaries. As we shall transform these objects, they are vectorized, so curves are approximated by polylines and regions by polygons. The rendering pipeline thus processes only point, line or polyline and triangle or polygon primitives. Modeling transformation places the object in word coordinates. This typically involves scaling, rotation and translation to set the size, orientation and the position of the object. in Word, objects meet other objects, and also the 2D camera, which is a rectangle with edges parallel with the coordinate axis. We wish to see the content of the window on the computer screen in another rectangle called the viewport. Thus, screen projection transforms the Word in a way that the window rectangle is mapped to the viewport rectangle. This can be done in a single step or in two steps when first the window is transformed to a square of corners -1, -1 and +1, +1 in a so-called normalized device space. Then another transformation transforms this normalized device space to physical screen space. Clipping removes all objects, either fully or partially, that are outside the camera window or the viewport rectangle, or alternatively of the -1, -1, +1, +1 square of normalized device space. The advantage of normalized device space becomes obvious here. Clipping here is independent of the resolution of the viewport or the size of the window, so can be easily implemented in a fixed hardware. Having transformed the primitives to the screen, where the unit is the pixel, they are rasterized. Algorithms find those pixels which can provide the illusion of a line segment or a filled polygon. Object-driven rendering is implemented with the help of the GPU. This figure shows which hardware is responsible for different stages of the rendering pipeline. The management of the virtual world and the vectorization of the objects are done by the CPU program written typically in C++. Vectorized point, line, and triangle primitives are copied to the GPU, where they are organized in vertex array objects, or VAOs for short. A VAO is a collection of arrays storing vertices and vertex properties. These arrays are called vertex buffer objects, or VBOs for short. The GPU feeds the vertex shader processor by the vertices and their attributes. A vertex shader processor gets one vertex with its attributes at a time and is responsible for computing the location of the vertex in normalized device coordinates. Additionally, the vertex shader may modify the attributes. The vertices output by the vertex shader form primitives like points, lines, or triangles, which are processed by the fixed algorithm pipeline of the GPU. This hardware clips the primitives, transforms them to screen space, and rasterizes them to produce a sequence of pixels. During these steps, vertex attributes are interpolated to generate attributes for each pixel that gradually change inside the primitive. For each pixel of this sequence, the fragment shader processor can determine the color of the pixel based on the interpolated attributes. The output of the fragment shader goes into the frame buffer. Vertex shader or fragment shader processors are programmed in GLSL, which stands for OpenGL Shading Language. The fixed algorithm pipeline cannot be programmed as it is hardwired. Vectorization approximates model objects with points, lines or polylines, and triangles or polygons. The main reason is that homogeneous linear transformations preserve only these types, and for the same reason OpenGL accepts only these primitive types. A positive side effect of this decision is that pipeline stages like clipping and rasterization should be solved only for points, lines, and triangles. Vectorization is trivial for parametric curves. The parametric range is decomposed and increasing sample values are substituted into the equation of the curve, resulting in a sequence of points on the curve. Introducing line segments between each subsequent pair of points, the curve is approximated by line segments. If the curve is closed, using the same strategy, a polygon approximation of the region can be found. If we had a software implementation of the output pipeline, we would work with line strips or polygons of arbitrary number of vertices. However, in GPU implementation, the hardware prefers records of fixed size. Therefore, polylines should be converted to line segments and polygons to triangles. The conversion of line strips to line segments is straightforward. However, the conversion of polygons to triangles is not that easy. A polygon is broken down to smaller polygons and eventually to triangles by cutting them along diagonals. A diagonal, by definition, is a line segment connecting two non-neighboring vertices that is fully contained by the polygon. We need to clip along diagonals only, since only this clipping guarantees that the resulting polygon will have less number of vertices than the original polygon. Thus, the method will terminate sooner or later in finite number of steps. If the polygon is convex, then any line segment connecting two non-neighboring vertices is fully contained by the polygon, because this is exactly the definition of convexity. Thus, all of these line segments are diagonals. This is not the case for concave polygons, when line segments containing vertices can intersect the edges or can fully be outside of the polygon. The good news is that all simple polygons, even concave ones, have diagonals, so they can be broken to triangles by diagonals. A polygon is said to be simple if its boundary is a single polyline that doesn't intersect itself. The sketch of the proof is shown here. Let us find a vertex that is extremal in one direction, for example, that has the maximum x coordinate. Consider the triangle defined by this vertex, the previous one and the next vertex. If this triangle doesn't contain any other polygon vertex, then the line segment connecting the previous and next vertices is a diagonal, so the proof is ready for this case. If this triangle contains vertices from the polygon, then let us find that vertex that is also extremal in this direction, and connecting this extremal to the original extremal vertex, we will obtain a diagonal. So the proof is complete. An algorithm based on this idea would search for diagonals, and having found one, the polygon would be cut into two, for which the same algorithm is executed recursively until all polygons become triangles. This algorithm has cubic complexity. Fortunately, there is a simpler and more efficient algorithm for triangulation. This triangulation algorithm searches for special vertices called ears. A vertex is an ear by definition if the line segment containing the previous and next vertices is a diagonal. According to the so-called two-ears theorem, every simple polygon of at least 4 vertices has at least 2 ears. So triangle decomposition should just search for ears, cut them until a single triangle remains. The proof of the two-ears theorem is based on the recognition that any polygon can be broken down to triangles by diagonals, at least any simple polygon. Let us start with one possible decomposition and consider triangles as nodes of a graph and add edges to this graph where two triangles share a diagonal. This graph is a tree, since it is connected because the polygon is just a single piece, and cutting every edge, the graph falls apart, so there is no circle in it. By induction, it is easy to prove that every tree of at least 2 nodes has at least 2 leaves, which correspond to 2 ears. For every step, we check whether or not a vertex is an ear. We can start anywhere. To do that, we check whether the line segment of its previous and next vertices is a diagonal. This is done by checking whether the line segment intersects any other edge. We can skip those edges that share a vertex with the tested diagonal candidate, since there cannot be a second intersection between two lines. We can skip also this and that, and the first serious case is the edge connecting vertices 3 and 4. A line segment is a convex combination of its two endpoints. So one way of testing two line segments for intersection is the solution of a system of linear equations stating that the intersection point is on both line segments. Solving this linear system of equations, we should check whether the intersection is inside of the line segments, that is, T1 and T2 parameters are in the 0,1 open interval. The test of a diagonal candidate should go for all edges. So for this particular case, we can conclude that there is an intersection between the red diagonal candidate and the green edge. So this diagonal candidate is not a diagonal, therefore vertex 1 is not an ear. When repeating the test for vertex 2, we can realize that the diagonal candidate connecting the previous and next vertices doesn't intersect any edge, but it is fully outside of the polygon. So additionally, we should also test for this. We can select an arbitrary point, for example the middle point of this candidate, and determine whether this middle point is inside the polygon. To do that, we should check when we are traveling to infinity from here, the number of intersections with the boundary is an odd number or an even number. If it's an even number like here, then the answer to the question is that the point is outside. If it was an odd number like here or here, when this number is 3, then the answer to this question is yes, the point is inside. Continuing the test with vertex 3, we can come to the conclusion that this diagonal candidate is indeed a diagonal because it doesn't intersect any of the edges and its middle point is inside. So we can cut this triangle, and the algorithm can be continued with the remaining polygon. So this is not a diagonal, but this is a diagonal, so vertex 2 is a ear, so a triangle can be removed and we end up with a single triangle, so the algorithm is terminated. There is a simple way to decide whether two line segments intersect each other. Let us compare the red line segment with the green line of the green line segment. If both endpoints of the red line segment are on the same side of the green line, then there is no possible intersection. The two red points must be on opposite sides of the green line. This is a necessary but not sufficient condition because the green line segment can still be completely on one side with respect to the red line. Clearly, the two green points must also be on the opposite sides of the red line. However, when both conditions are met, intersection is inevitable. In order to check whether 2 points are on the two opposite sides with respect to a line, we can substitute the points into the implicit equation of the line. If they are on opposite sides, signs of the dot product are different. The second option would solve this problem by realizing that the cross product results in vectors of opposite directions if the angle between the vectors changes the sign. After vectorization, the first relevant step of rendering is placing the reference state primitives in Word, typically scaling, rotating, and finally translating its vertices. Recall that it is enough to execute these transformations to vertices because points, lines, and polygons are preserved by homogeneous linear transformations. These are also affine transformations in 2D rendering, and the resulting modeling transformation matrix will also be an affine transformation. In this case, the third column of the matrix is 0, 0, 1. Then the other matrix elements have an intuitive meaning, namely they specify what happens with basis vector I, j, and the origin itself. Scene projection maps the window rectangle, which is the camera in 2D, onto the viewport rectangle, which can be imagined as the photograph. This simple projection is usually executed in two steps. First, transforming the window onto a normalized square, execute clipping, and then in the second step transforming the square to the viewport. Transforming the window to normalized device space, that is an origin-center square of corners -1, -1, and +1, +1, is also a sequence of two transformations. The first one is the view transformation and is usually denoted by V, which is a translation that moves the center of the camera window to the origin. The translation happens with the negative center of the camera window, so after translation, the camera window center will really be in the origin. The second transformation is the projection and is usually denoted by P. It is a scaling that modifies the window width and height to 2. Projection transformation scales by 2 divided by the width in direction x and 2 divided by the height in direction y. So at the end of the scaling, indeed, the edge size of the square will be 2. A 2D camera is thus represented by the center called W center and the size called W size of the camera window. We use W initials since these data are interpreted in word coordinates. A 2D camera is associated with view and projection transformations as well as their inverse. Zoom and pan operations are just the modifications of the size and the center, respectively. Having transformed the objects to normalized device space, the next step is clipping that removes object parts outside of the camera window or the viewport. Clipping is executed usually in normalized device space where the camera window or the viewport is a square of corner points -1, -1 and +1, +1. Therefore, for a point to survive, its x and y coordinates must be between -1 and +1. To be general, we denote the limits by x minimum, x maximum, y minimum, and y maximum. A point is preserved by clipping if it satisfies these four inequalities. X is greater than x minimum and smaller than x maximum, while y is greater than y minimum and smaller than y maximum. A point is inside the clipping rectangle if it is inside of four half planes defined by these four inequalities, since the clipping rectangle is the intersection of the four half planes. The concept of clipping on half planes is very useful when line segments or polygons are clipped, since testing whether or not the two endpoints of a line segment or vertices of a polygon are outside, the clipping rectangle cannot really help to decide whether there is an inner or outer part of the primitive. So for example here, we have a line segment when both endpoints are outside of the clipping rectangle, but there is a part of the line segment which is still in. This situation cannot happen when we clip on the half plane, because if both endpoints of the line segment are in with respect to a half plane, then all points must be in, and similarly, if both endpoints are out, then the complete line segment must be out. Clipping on a rectangle is replaced by a sequence of 4 clipping steps on 4 half spaces. First, clipping on half space x is greater than x minimum, then on half space defined by y is greater than y minimum, the result goes into the clipping space corresponding to half space of equation x is smaller than x maximum, and finally to the half space defined by y is smaller than y maximum. And we have the result that contains those primitive paths which are in the clipping rectangle. Let us consider a line segment and its clipping on a single half plane. For example, the half plane of equation x is smaller than x maximum. If both endpoints are inside, then the complete line segment is inside, since the inner region is a half plane which is convex. If both endpoints are outside, then the line segment is completely outside, since the outer region, which is also a half plane, is also convex. If one endpoint is inside while the other endpoint is outside, then the intersection between the clipping line and the line segment needs to be calculated, and the point that is outside is replaced by this intersection. For the intersection calculation, we take the parametric equation of the line segment, which expresses the line segment points as the convex combination of the two endpoints, and also the equation of the clipping line. This system of linear equations is solved, and we obtain the intersection point. Polygon clipping is traced back to line clipping. We consider edges of the polygon one by one. If both endpoints are in, then the edge will also be part of the clipped polygon. If both of them are out, then this edge is completely removed from the clipped polygon. If one point is in while the other endpoint is out, then a new vertex is added to the clipped polygon, which is the intersection of the edge and the clipping line. The input of the algorithm is an array of vertices and the number of points in this array called n. The output is also another array of vertices and the number of vertices contained by this array. Usually we assume that edge I has endpoints pi and pi plus 1. However, the last edge is an exception, since its endpoints are p n-1 and p0. So either the last point should be handled in a special way, or we can store the first element once again at the end just to avoid over-indexing the array. The algorithm goes as follows. So we visit vertices and edges one by one, test whether the starting point is in, and if it is in, it is added to the output array. And before we step to the next edge, we just check whether this edge has an intersection with the boundary. Since pi was in, there is an intersection if pi plus 1 is out. This is not the case here, so we just move to the next cycle. This point is in again, so this is added to the output array, but the next point will be out, so there is an intersection between the edge and the clipping line, and this intersection is also added to the output. Then we consider the next vertex P2, which is outside, so it is not added to the resulting array, but we check whether the next point is in, so there is an intersection between the edge and the clipping line. This is not the case here, so nothing is added to the output array. For P3, it is out, and the next point will also be out. When I is 4, then this point is out, so we are in this branch of the else statement, but the next point is in, so an intersection calculation should take place and the result is added to the output. Finally, we visit P5, which is in, so it is added, and we also check whether this point and the next point, which is point 0 in this particular case, define an edge which has an intersection. This edge has no intersection, so we are done. In Cartesian coordinates, the limits of clipping are -1 and 1 in normalized device coordinates. We shall adopt this requirement for the third coordinate as well when clipping is extended to 3D. Transformation to normalized device space is a homogeneous linear transformation which may not be affine, so it may happen that the result is in real homogeneous form where the fourth homogeneous coordinate is not 1 anymore. To prepare for this general case, clipping operation is executed in homogeneous coordinates. So we should find the equation of clipping volume in homogeneous coordinates. Substituting Cartesian coordinates x, y, and z by homogeneous coordinates, we know the correspondence. X is xh divided by h, y is yh divided by h, and z is zh divided by h. We can establish a system of inequalities. To make it simpler, we wish to multiply both sides by the fourth homogeneous coordinate h. However, an inequality cannot be multiplied by an unknown variable, since should this variable be negative, the relations must be negated. The further calculations should be done separately for positive h and negative h. Alternatively, we can declare another requirement that h can only be positive, which simplifies the problem, and OpenGL also uses this simplification. This requirement seems to be a kind of arbitrary, but is typically true in 2D graphics when homogeneous coordinates are obtained by extending Cartesian coordinates with an extra value, and that value is 1. So h is indeed positive. In 3D, h is greater than 0 corresponds to the requirement that the volume must be in front of the eye or the camera, so we can accept this extra requirement in 3 dimensions as well. So we check just this system of inequalities to decide whether a point is in or out. The collection of these inequalities defines a cube. A point is inside the cube if all inequalities are met. So we clip onto 6 half spaces, one after the other. The intersection of these half spaces is a cubical view frustum. Each half space is associated with a single inequality, and the border plane of the half space is defined by the equation where the smaller relation is replaced by equality. We consider here just one half space of inequality xh is smaller than h, where the boundary is the plane of equation xh is equal to h. The half space inequality is evaluated for both endpoints. If both of them are in, the line segment is completely preserved. If both of them are out, the line segment is completely ignored. If one is in and the other is out, we consider the equation of the boundary plane. This is xh is equal to h, and the equation of the line segment, which is the linear combination of the two endpoints in homogeneous coordinates, and solve this system of linear equations for unknown parameter t. Substituting the solution back to the equation, we get homogeneous coordinates of the intersection point. The intersection point replaces the endpoint that has been found outside. Having executed the clipping step, homogeneous coordinates are converted to Cartesian coordinates, executing the homogeneous division. Because of clipping, all 3 Cartesian coordinates are between -1 and 1. The last transformation maps this normalized device space coordinates to real pixel space so that the point -1, -1 in x and y goes to the lower left corner of the viewport, and 1, 1 in x and y to the upper right corner. OpenGL transforms the third coordinate as z is equal to z plus 1 divided by 2, so the -1, 1 interval is also mapped to 0, 1 in the third coordinate. The viewport lower left corner width and height are specified by the GL viewport function in OpenGL. Before starting the discussion of rasterization, it is worth looking at the pipeline and realizing that the rasterization uses a different data element, the pixel, while phases discussed so far work with geometric primitives. A primitive may be converted to many pixels, thus the performance requirements become crucial at this stage. In order to maintain real-time frame rates, the process should output a new pixel in every few nanoseconds. It means that only those algorithms are acceptable on this level that can deliver such fantastic performance. Line drawing should provide the illusion of a line segment by coloring a few pixels. A line is thin and connected, so pixels should touch each other, should not cover unnecessarily wide area, and should be close to the geometric line. If the slope of the line is moderate, that is, x is the faster growing direction, then it means that in every column exactly one pixel should be colored, and that pixel should be the closest to the geometric line. The line drawing algorithm in this special case iterates on columns and finds the coordinate of the geometric line using the explicit equation of the line, and finally finds that integer which is closest to the geometric line. This works. We can implement a simple algorithm, but for every pixel it requires a non-integer multiplication and an addition, and finally a non-integer to integer conversion, which are too much for a few nanoseconds. So we should modify this algorithm, preserving its functionality but getting rid of the complicated operations. The algorithm transformation is based on the incremental concept, which realizes that a linear function is evaluated for an incremented x coordinate. So when x is taken, we already have the y coordinate for x minus 1. The fact is that it is easier to compute y of x from its previous value rather than directly from x. The increment is m, the slope of the line, thus a single addition is enough to evaluate the line equation. This single addition can be made faster if we use fixed point number representation and not floating point format. As these numbers are non-integers, as m is less than 1, the fixed point representation should use fractional bits as well. It means that an integer stores the tth power of 2 multiple of the non-integer value. Such values can be added as two integers. The line drawing algorithm based on the incremental concept is as follows. First, the slope of the line is computed. The y coordinate is set according to the endpoint. This y stores the precise location of the line for a given x, so it is a non-integer. In a for cycle, the closest integer is found, the pixel is written, and according to the incremental concept, the new y value for the next column is obtained by a single addition. Rounding can be replaced by a simple truncation if 0.5 is added to the y value. The fixed point representation of the same algorithm is shown here. And I have to tell you that this incremental principle is rather old. Even Babbage used in his so-called difference engine in the 19th century, which was a mechanical computer, and it was able to evaluate polynomials using this incremental principle. This algorithm can be implemented in hardware as well with a simple counter that generates the increasing x values for every clock cycle. For y, we use a register that stores both its fractional and integer parts. The y coordinate is incremented by m for every clock cycle. For triangle rasterization, we need to find those pixels that are inside the triangle and color them. The search is done along horizontal lines of constant y coordinate. These lines are called scan lines and rasterization as scan conversion. For a single scan line, the triangle edges are intersected with the scan line and pixels are drawn between the minimum and maximum x coordinates. The incremental principle can also be applied to determine the scan line and edge intersections. Note that while the y-coordinate is incremented by 1, the x-coordinate of the intersection grows with the inverse slope of the line, which is constant for the whole edge and thus should be computed only once. Again, we have an algorithm that uses just increments and integer additions. Rasterization selects those pixels that belong to an object. The only remaining task is to obtain a color and write it into the selected pixel. There are different options to find a color. It can be uniform for all points, or alternatively, colors or any property from which the color is computed can be assigned to the vertices. Then, the colors of internal pixels are generated by interpolation. Finally, we can also define the object vertices on a pattern image called texture. The pattern or texture is then mapped on or wallpapered onto the object. 2D texture mapping can be imagined as wallpapering. We have a wallpaper that defines the image or the function of a given material property. This image is defined in a so-called texture space in a unit rectangle. The wallpapering process will cover the region with this image. This usually implies the distortion of the texture image. To execute texturing, we have to find a correspondence between the region and the 2D texture space. After vectorization, the region is a triangle mesh, so for each triangle, we have to identify a 2D texture space triangle which is painted on the model space triangle. The definition of this correspondence is called parameterization. A triangle can be parameterized with an affine transformation, which means that x and y are linear functions of texture coordinates u and v. This can be seen by counting the number of unknowns in a pair of linear functions and counting the number of constraints for an affine transformation to map one given triangle onto another given triangle. The number of unknowns a, b, c with subscript x and y is 6, and so are the number of constraints since a triangle has 3 vertices and the requirement 2 points are identical means 2 equations, one for x and one for the y coordinate. Screen space coordinates, on the other hand, are obtained with affine, or to be more general, with homogeneous linear transformation from model space coordinates x and y. Thus, mapping between the texture space and screen space is also a homogeneous linear transformation. The triangle is rasterized in screen space. When a pixel is processed, texture coordinates u and v must be determined from pixel coordinates x and y, which requires the execution of the inverse of the homogeneous linear transformation connecting the texture space to the image space. If we need Cartesian coordinates, homogeneous division should also take place. In other words, homogeneous coordinates capital U, V, and H depend linearly on coordinates x and y. Cartesian texture coordinates are obtained with executing the homogeneous division. The crucial problem is then the linear interpolation of the color, properties in general, or homogeneous texture coordinates for internal pixels. The interpolation must be fast, as we have just a few nanoseconds for each pixel. Let us denote the interpolated property by u. Linear interpolation means that u is a linear function of pixel coordinates x and y. So we have to evaluate a linear function ax plus b y plus c, which requires 2 multiplications and 2 additions. This can be reduced to a single addition if we use the incremental concept and focus just on the difference between the U values of the current pixel and the previous pixel. Such incremental algorithm is easy to be implemented directly in hardware. A counter increments its value to generate coordinate x for every clock cycle. A register that stores the actual U and V and age are needed, which are updated by the constant increments with 3 adder units. From these homogeneous coordinates, the Cartesian UV texture coordinates are computed with 2 divisions. So finally, there is only one problem left: how to obtain the increment A. Here we show 2 different approaches, but obviously the result is the same. One way of determining it is to satisfy the interpolation constraint at the 3 vertices. It means that substituting the xy coordinates of the vertices into the linear expression, we should obtain the value to be interpolated at the 3 vertices. So this is a system of linear equations for unknown parameters a, b, and c. The other way is based on the recognition that we work with the plane equation where x, y, and u coordinates are multiplied by the coordinates of the normal vector of the plane. The normal vector, in turn, can be calculated as the cross product of edge vectors. Rasterization visits pixels inside the projection of the triangle and maps the center of the pixel from screen space to texture space to look up the texture color. This mapping will result in a point that is usually in between texel centers. Suppose we step 1 pixel in image space. Consequently, the transformed UV texture coordinates also change. This change can be smaller than a single texel or bigger than a texel. Looking at this situation from the other direction, the first case is when the texel covers multiple pixels. This is called magnification. The second case is when many pixels are mapped to a single pixel and the pixel color is determined by that pixel which is lucky enough to be mapped onto the pixel center. This case is called minification. From signal processing point of view, the texture can be considered as a signal which is sampled at pixel centers. In the optimal case, 1 texel corresponds to 1 pixel. In case of magnification, the texels will be large, which is a kind of oversampling. In case of minification, texels are too small and are undersampled, and the result will be a mess or noise. In case of oversampling or undersampling, artifacts occur. Magnification makes the individual texels obvious. Minification converts the pattern to noise. When these images were rendered, the pixel is colored with the texel covering its center. This sampling strategy is called the GL nearest strategy in OpenGL. The sampling strategy can be set with the GL text parameter function, and it can be done separately for the case of magnification and minification. The solution for the undersampling problem is filtering. Instead of mapping just the center of the pixel from image space to texel space, the complete pixel rectangle must be mapped to texture space, at least approximately. And the average of texel colors in this region should be returned as a color. However, it would be too time-consuming to identify those texels that are inside of this general quadrilateral. One efficient approximation is to prepare a texture not only for its original resolution, but also in half resolution, quarter resolution, and so on, where a texel represents the average color of a square of the original texels. So we approximate the general region by predefined squares. These sampled or downsampled images form a hierarchy, also called mipmap. During rasterization, OpenGL estimates the magnification factor and looks up that prepared downsampled texture which corresponds to this magnification factor. Indeed, with MIP mapping, artifacts disappear. MIP mapping can be selected with this GL linear MIP map nearest texture sampling strategy. There is another simpler filtering scheme which is particularly good for magnification artifacts. In other words, to reduce oversampling artifacts. In this method, when a pixel center is mapped to texture space, not only the closest texel center, but all 4 texel centers are taken into account that enclose the transformed texture point. Filtering happens using a bilinear strategy. As these images demonstrate, bilinear filtering smears the ugly texel edges. Between the output of the fragment shader and the raster memory, there is a final hardware unit that is responsible for merging the new color values. The simplest case is rewriting the old color by a new one. With this merging unit, other combinations are also possible. The merging unit is enabled with the GL enable switch and disabled with GL disable switch applied to the GL blend constant. GL blend function specifies the current way of blending or compositing. This particular solution is very popular since it simulates transparent colors where the transparency is the complementer of the opacity defined by the alpha channel of the color.